So the copper is a solid at the beginning.
Mm-hmm.
Okay, what about the aluminum?
A solid.
So we have two solids at the beginning of the reaction?
I thought that was strange too, but when I Googled what copper sulfate is, it says a solid.
It is a solid. Is it a solid in this experiment?
No.
Not really. So copper sulfate is indeed a solid. What kind of compound is it?
Ionic.
It's an ionic compound, yes. So we have copper sulfate, and that is an ionic compound. So is it a solid, though, in this particular experiment? We said, no, it isn't. So in what state is it?
It's a liquid.
But so it's in a liquid state, but would we say that the copper, I mean, it's in a liquid, but do we say that the copper sulfate itself is a liquid? How do we actually define its state in that? So, because we're going to put that in water. And what happens when we put an ionic solid into water? I mean, it dissolves, yes, but what happens to the ionic compounds? The elements in the ionic compound, what happened to them?
They separate.
They what?
Separate.
They separate. Yes, they do. They do separate. And when they do separate, what happens to them? So you have a compound, an ionic compound. And what does it mean to have an ionic compound, actually? What's the difference between an ionic compound and a covalent compound?
That means that one is the ionic compound has a nonmetal and a metal, and covalent is two nonmetals.
Right. And what else? So what does that? So what does that do for us if we have a metal and a nonmetal together in an ionic compound? What else does that tell us about? I mean, what does ionic compound mean, other than if there's a metal and a nonmetal?
That means there's going to be a cation and an anion because they're not sharing electrons.
Bingo, exactly. It means they're charged, right? It means we have a cation with a positive charge, and we have an anion with a negative charge. So in copper sulfate, which one is the cation and which one is the anion?
Sulfur is the cation.
Sulfur?
Yes. And the oxygen is the anion.
Sorry, which is the anion?
Oxygen.
Oxygen. Okay. What about the copper?
Copper is cation.
So we have two cations?
I mean, in the sulfur, in the right side, the compound, they have one cation and one anion.
Right. So this compound has one cation and one anion. So which is the one cation?
On the you mean on the right side?
No, just this whole thing.
Oh, just whole thing. I think the copper is the cation.
Yep.
And the white part, the whole part is the anion.
That's right. SO4 all by itself is called sulfate. It is a polyatomic anion, so it's negatively charged. So we know that copper has a positive charge, and we know that sulfate has a negative charge. And when we put them in the water, they separate. And what what sort of state of matter do we put? You know, like if copper is a solid, we put S next to it. Water is a liquid at room temperature, we put an L next to it. What do we put next to the copper and the sulfate when they're dissolved in solution and they're charged? What state of matter is that?
Is it the AQ?
Yes, it is. Excellent. Yeah, it means it's dissolved in water. And so we would put AQ next to them. Very good. Now we have to figure out, so that's what we have in the copper sulfate solution. We have a positively charged copper cation, and we have a negatively charged polyatomic sulfate anion. But do we know what the charges are on the copper and the sulfate? What's the charge on the copper?
Positive 2.
How do we know that? Is copper is, what kind of metal is copper?
Is a
Where is it on the periodic table? So when you look at the periodic table, where are you going to find copper?
a transition metal.
Yes, it's a transition metal. So do we know what its charge is going to be just by looking at it?
Yeah.
We do? Because sometimes it's +1 and sometimes it's +2. How do we know it's +2 in this instance?
Because the sulfate is negative 2.
Exactly. Excellent. Yeah, we know that the sulfate is always -2. The sulfate ion is always, always, always -2. It's never anything else. So we also know that ionic compounds need to be balanced. Their total charge needs to be balanced. So if there's one sulfate ion that's -2, it's always, always, always -2, and there's only one copper ion, we automatically know that that can't be copper 1. It has to be copper 2. So the charge on copper is +2. So that's, so far, we have this part of the reaction. We have copper sulfate aqueous, and that means copper +2 and sulfate -2. And what's the other thing that we're going to be putting into the reaction? So we have copper +2, we have sulfate -2, and what else do we put in the reaction? What's our other reactant?
Aluminum.
Aluminum, right. And what state is the aluminum in?
Solid.
It's a solid, that's right. So what's the charge on the aluminum?
No charge.
There isn't, right, it's a metal. And metal, when it's just by itself, as a solid, doesn't have a charge. It's only when it reacts with a non-metal that it becomes positively charged. So these are our two reactants. What are our products going to be?
Copper and aluminum sulfate.
Oh man, you guys are crushing this today. Yeah, so we're going to get copper. And in what form is the copper going to be?
Solid.
Just a solid, right. And aluminum sulfate, man. So there's aluminum, there's sulfate. What's going to be the formula for aluminum sulfate? What charge does aluminum take on when it goes into solution? How do we figure that out?
+3.
+3, you're absolutely right. How did you know that?
I know that from the periodic table.
There you go. There you go. When we look for aluminum, aluminum is right there. So aluminum is there. It's in group 3, basically. So, and it's not a transition metal. So aluminum always has a +3 charge when it goes, when it becomes a cation. Always, always, always. It's never anything else. So what's going to be our formula for aluminum sulfate? If you have aluminum +3 and you have sulfate minus 2, what's going to be the formula for aluminum sulfate here? Because that doesn't look right. AlSO4 is not the correct formula for aluminum sulfate.
It's going to be Al2SO43.
Oh man, so how did you get that?
So since the aluminum has a +3 charge, you would multiply that by 2 to get +6. And then since the sulfate has a -2 charge, you have to multiply that by 3 to get -6. So then they cancel out.
Man, you guys sure you need me to doing this? Because it seems like you know this stuff already. You're absolutely right. So you want to balance the charges. So if aluminum's +3 and sulfate's -2, the quickest way to have them equal plus and minus charges is to have both have 6. So that formula will be Al2SO4 3. So let's put it all together. So this is going to be our complete reaction. So we've got copper sulfate plus aluminum makes copper plus aluminum sulfate. This is aqueous. That's a solid. That's a solid. This is aqueous. So that's our full reaction, right? We're taking aqueous copper sulfate, we're adding solid aluminum to it. The reaction takes place, the single replacement reaction takes place, where basically the aluminum and the copper switch places. The aluminum was a solid, and the copper was an ion in solution with sulfate, and they switch places. Now the copper becomes a solid, and the aluminum becomes an ion in solution. But what else do we need? So we figured that part out. What else do we need to do with this reaction before we can start our experiment?
Balance it.
Oh, yeah, we do. We have to have a balanced reaction, because I mean, basically, what is the point of this reaction? What are we trying to calculate at the end? What's the thing we're trying to calculate at the end of the experiment? What are you measuring at the end of the experiment? The last thing you measure at the end.
Percent yield.
Right. Percent yield of what?
Of copper.
Right. We're going to measure the mass of the copper and see if it's the amount we predicted we would get. So percent yield. So we're going to have to figure out the mass of the copper and try and figure out what would be the maximum amount of copper we could produce if everything went perfectly. But how are we going to predict that if we don't have a balanced reaction? We need to have a balanced reaction. So let's start balancing this thing. So when I look at it, pretty much the only thing that's balanced is the copper, because there's one on the reactant side, there's one on the product side. Nothing else is balanced. So who wants to take over from here? How are we going to balance this thing?
When I did it in the pre-lab, I got 3CuSO4 plus 2Al, and then the arrow, 3Cu plus Al2SO43.
Right, so we need 3 sulfates. So remember, sulfates don't separate. The sulfur and the oxygen do not separate. That's a polyatomic ion. It stays together. So we can treat it as a single unit. And we have 3 of them over here. So we're going to need 3 of them. Oops, hate when that happens. So we're going to need 3 of them over here. That means we now have 3 coppers, 3 copper atoms on the left side. So now we're going to need 3 coppers on the right side. And pretty much the only thing left that we need to balance is the aluminum. And there's 2 of them as products, 2 aluminum ions as products. So to make 2 aluminum ions, we're going to need 2 aluminum atoms. on the left side. Now, later you're going to find out this is what's called a redox reaction. Anybody know what a redox reaction is? Just kind of curious. Have you heard of that before? What is so okay, no. So redox means reduction oxidation. So it's an oxidation and reduction reaction. And what that means is that the charge on copper is being reduced. The charge on copper over here, we have 3 of them, and they were +2. The charges on all those atoms, on those ions, is going to be reduced to 0 over here. Aluminum, on the other hand, is going to be oxidized. Its charge is going to go up. It's going to go from 0 on this side to +3 on this side. And they're going to have 2 of them. How many electrons are going to go from the aluminum to the copper? Total electrons. Because that's what's actually happening in this reaction. Electrons are moving from the aluminum and they're going to the copper. What's the total number of electrons that are going to be transferred? Think about it for a minute. You have 3 coppers at +2 and they all go to 0. On the other hand, you have 2 aluminums at 0 and they go to +3. How many electrons move from one to the other?
6.
6, exactly. So this reaction is a transfer of 6 electrons from aluminum to copper. That's the actual reaction you're doing. It's an electron transfer reaction where the aluminum is being oxidized, the copper is being reduced. So now that we have a balanced reaction, and we've balanced everything, we've balanced the atoms, we've balanced the charge, and we've balanced the electrons. So now we can figure out what our potential yield is going to be. So how are we going to figure that out? How do we figure out our potential yield, or what we call our theoretical yield of aluminum? What do we measure first? What's like the pretty much the first thing we measure during this reaction?
Is it the molar ratio?
Well, before you even do that, what do you measure about the aluminum?
How many grams?
Right, we're going to take the mass of the aluminum in grams. Now, how can you now I'll get back to your molar ratio in a minute, it's an excellent point. But how do we take the mass of the aluminum and from that figure out what my potential mass of copper is? How do I do that? Is it just, if I have 3 grams of copper, I'm going to get and 2 grams of aluminum? Is that how that works? How does that work?
The 3 and the 2 are the number of moles, right?
Right. Right. So what's the first thing we want to do with our mass of aluminum?
Find its mass in grams.
We find the mass. So we find the mass in grams, and then what do we do with that information? What do we need to convert it to? Because you've informed me that all these numbers here are mole numbers. They're not grams. It's not 3 grams of copper sulfate plus 2 grams of aluminum give us 3 grams of copper. That's not, it's moles. So what do we do with our mass of aluminum? Right, John, we convert grams to moles. So I want moles of aluminum. How am I going to do that? I need to multiply this by something that at the end of it, I get moles of aluminum. How am I going to do that? What do I multiply this mass of aluminum by to get moles out? You remember my sort of basic rule about converting units. When I have a unit that I don't want and I want to convert it into something else, what I do is that I multiply it by something that has the unit I want in the numerator and the unit that I want to get rid of in the denominator. So what am I going to multiply this by? What do I put in the numerator? What do I put in the denominator to go from mass of aluminum to moles of aluminum?
6.022 times 10 to the 23rd.
Excuse me?
6.022 times 10 to the 23rd.
So that'll give me, so if I do that, that's the number of atoms, right? That'll give me a unit of gram atoms, grams times atoms. I don't want gram atoms. I don't even know what that is. I want grams at the beginning, but at the end, I want moles. So gram atoms isn't really going to get me where I need to go. There's something else I need. I need. Right, so John tells me that 1 mole of aluminum happens to equal 26.98 grams. What do I do with that information?
Put the one with the grams on the bottom.
Right. So remember, whenever you convert a unit, when this conversion factor, you just basically what you're doing is you're multiplying by 1. Whatever's in the numerator has to equal what's on the denominator because you're multiplying something by 1 so that it's equal. What's equal? 1 mole is equal to 26 or around 27 grams. Those two things are equal. I want moles. So I'm going to put moles on the top. So 1 mole of aluminum is equivalent to 26.98 grams. So then you take your initial mass of aluminum, you cancel out grams when you multiply by 1 over 26.98, and then you get moles of aluminum. So great. So now we've got moles of aluminum. How are we going to get to moles of copper from that? That means I need to multiply it by yet another set of units to go from moles of aluminum to moles of copper. So how do I go from moles of aluminum? I want to multiply that by something to get to moles of copper.
Is it the ratio?
The molar ratio. The molar ratio from where?
From the balanced chemical equation, which would be 2/3.
Bingo. Right. I put moles of copper on the top because that's what I want. So moles of copper on the top, moles of aluminum on the bottom. And I look at my balanced reaction and I've got moles of copper is 3. My moles of aluminum are 2. So don't rush it and say it's 2/3 because it actually isn't. It's 3/2 because we want, remember, aluminum is going to be on the bottom. Copper is going to be on the numerator because that's what we want. So however many moles of aluminum we figure we have from our sheet of aluminum foil, at the end, if everything goes perfectly, we would have 3/2 moles of copper. So now we have moles of copper. Are we going to be measuring moles of copper like at the end of the experiment? What actually are we going to be measuring at the very end? I don't know how to measure moles of copper. I don't have a measure. I don't have a piece of equipment, and you don't have a piece of equipment that measures moles. So what are we going to do?
Convert it back into grams.
Right, we need to convert it back to grams because your scale measures grams. It doesn't measure moles. Scale doesn't know what a mole is. It knows what a gram is though. So when you figure out how many moles of copper you should get if everything goes perfectly, 100% transformation, you need to multiply that by something to get grams of copper. And what are we going to multiply moles of copper by to go back to grams? Remember, now I want grams on the top. So I'm going to put grams on the top, and I want to get rid of moles. So I'm going to put moles on the bottom. So I'll get rid of moles. I'll be left with grams. So what do I put on the numerator?
63.546.
What's that?
That's the atomic mass of copper.
Right, that's the atomic mass of copper. So 63.55, we'll say 63.55. So you would expect, since copper is heavier than aluminum and you get 3 moles of it instead of 2, you should actually get more mass out than you put in, because the copper is a bigger atom than aluminum. So if you put in like a gram of copper, you should get more than that out, hopefully. So that'll give us what we call our theoretical yield of copper. So if everything goes perfectly, we'll get that much copper, but you're not. I mean, nobody gets 100% yield. So we actually need to calculate percent yield. And what does that mean? Percent yield.
That's your theoretical yield divided by your actual yield.
So we put the theoretical on the top or the actual on the top?
Oh, you put the actual on the top.
Right. We put our actual yield on the top and our theoretical maximum on the bottom. Oop, nice spelling. Theoretical on the bottom, and then multiply that by 100. So actual what? What are we going to be putting there? Grams, moles, what are we going to be putting there?
Grams?
Yeah, because chemists, when we talk about a yield of a reaction, we don't talk about moles. Like, so, you know, if your advisor, like in a lab or something, said, you know, what was your yield on that particular reaction, you'd say so many grams or so many milligrams or whatever it is you could get back. So we take our actual yield in grams, divide it by what we calculated for a theoretical yield, and that'll give us a percent yield. So someone asked previously, now if in our reaction, so I won't bother to balance it, but plus copper. So how do we know that this is going to go to completion? How do we know that all of the copper, all of the aluminum is going to get converted to copper? How do we guarantee that that happens? If you want one of the reactants to be completely used up and turned into product, what do you need to know about the other reactant? I want to make sure that every single atom of aluminum gets converted to copper. What do I need to do with the copper sulfate to ensure that that happens? can I just throw any amount of copper sulfate in there and it will automatically convert everything to copper? What do I need to ensure?
I think we need to have more aluminum.
More aluminum. So there should be more aluminum than copper sulfate.
Yeah, I mean, in the when the reacting is finished, we need to have we need to see the aluminum. There has a little bit aluminum. I mean,
But if there's a little bit of aluminum left over, that means we haven't converted all of it to copper. We want to convert all of it to copper. So how do I ensure that with this reaction? How do I make sure that that happens? Because you don't want any aluminum foil left over. And in the procedure, they give you a definite limit. You want to have at least this much aluminum, but you don't want to have too much. Why don't you want to have too much?
If there's too much, it won't all be used and it won't be the limiting reactant anymore.
Right. If you have too much aluminum, basically you'll use up the aluminum until all the copper sulfate, all the copper has been converted to copper solid. Once there's no more copper ions in your solution, the reaction stops and you're left with aluminum that hasn't been converted. So if we want to convert all the aluminum, how do we ensure that that happens? How much copper sulfate am I going to need to add to make sure that that happens? Any amount? Doesn't matter how much we add? What do we think? I'm just going to start calling on people. Francesca, what do you think? Do I need to worry about how much copper sulfate I add?
Well, I'm just guessing, but I know in like the lab manual, it says that you need approximately 100 milliliters of it. But my guess is that it has to be kind of proportional, like comparing it to the balanced equation.
Right, it does need to be proportional. Exactly. So if I know how many moles of aluminum I have, and I can figure out how many moles of copper sulfate I would need because of my balanced reaction, how do I ensure that I still have copper sulfate left over at the end? There's a basic word I'm looking for. It starts with E. I want to have that much copper sulfate. Oh man, Wheel of Fortune, you guys would stink at Wheel of Fortune.
Is excess?
Excess, that's what, exactly, that's what we're looking for. We need an excess. In any reaction, basically you're going to have an excess of one of the reactants, and the other one is going to be limiting. Now, what's the definition of a limiting reactant?
The reactant that you run out of.
Right. You run out of the limiting reactant. And so we call it the limiting reactant because it limits the amount of product you're going to get. You can't get any more product than the limiting reactant allows you to. And that's what we're counting on here. We're counting on aluminum being the limiting reactant because all of it will be converted to copper. And so it will limit exactly how much copper we get. So we have to have an excess of copper. And we can go insane and have like, twice as much as we need or 3 times as much as we need. But around 100 mils of this should be enough. And you can calculate it. Should be enough that it's in excess of the number of moles required. Now, when you see your copper, will you get me the blue bottle there, Raj, please?
Sure.
When we look at the bottle here, gracias. When you look at the bottle here, what does it say on it as far as how much copper sulfate is in it? It says 1M. What does that mean? It says 1M copper sulfate. What does that even mean? What's capital M? It doesn't mean 1 mole. You're close, but that does not mean you have a mole of copper in here, but you're close. Think of it though, because it's a solution, we have the capital M. So what does that mean? It does have the M has something to do with moles, yes, but you have to take into consideration that it's a solution. So what does capital M stand for? Molar. That's right. What does molar mean? It means it's a 1 molar solution. But what does molar mean? It's a measure of molarity. Yep, we're getting closer. What's molarity mean? Molarity is a unit of something.
Moles per liter.
Bingo. It's a measure of concentration. So this tells me how the 1M tells me how concentrated this solution is in terms of moles over liters. Because this is what I need. When I'm measuring a liquid, I don't measure it in grams. Right? What do we measure liquids in? In volume. So this tells me how many moles of what's in this thing, in this case, copper sulfate, how many moles of copper sulfate for every liter of solution I have. So if I have about 100 milliliters, which is this, that's equivalent to about 1/10 of a liter, right? 100 milliliters is 1,000 milliliters in a liter. So 100 milliliters is about 1/10 of a liter. That means how many moles of copper sulfate are in this bottle?
10 more.
10 moles. So remember, I have 1 mole for every liter. I only have 1/10 of a liter. How many moles will that be?
A 10th.
1/10, right. So I get rid of liters. I'm left with moles. 1 times 0.1, 0.1 moles. So that's approximately how many moles of copper sulfate are in this bottle. So you can work out, that should be more than the number of moles of copper we're going to need for this reaction. Because if it isn't, it's not going to go to completion. Okay? So I am going to, any other questions before we get going? Oh, I have one note I wanted to mention. In the instructions, I noticed that, oh wait a minute, sorry, I didn't share that with you. I noticed that there is an instruction they should give you that they don't. So in the reaction here, we have, so they want you to measure out the number of the volume of the copper sulfate. That's fine. They want you to measure out the mass of the aluminum foil. That's good. You do the reaction. You decant off some of the solution that's left over. You wash the copper that you get out at the end with water, and then you filter it. But what they don't mention, which is a really good idea, you should take the mass of your filter paper before you start filtering it. Because what we're going to do is take the mass of this filter paper. So here's our filter paper that we're going to do the filtering in. Take the mass of the filter paper before you start filtering. And then at the end, after you've washed it and dried it, you'll have the filter paper plus the mass of the copper. Then all you need to do is just reweigh it. In this particular, because I did this experiment with my 410 class last night, and they basically, I neglected to mention this, because in the actual protocol here, they want you to scrape the copper off the filter paper and onto something else. That's just going to lead to more loss of your product, and it's another unnecessary step. In a real lab, what you would do is you would just measure the mass of the filter paper plus your product. There you go. That's the mass of your product. Okay, so remember, that'll save you a step and a lot of anguish. So just measure the mass of your filter paper before, measure the mass of the filter paper after, and the difference will be the mass of your copper. It'll save you some headaches. All right. Any other questions before we go? I'm going to turn off the camera for a minute, get situated, and I have a brilliant 11-year-old chemist who's going to help me with the reaction. Yeah, there he is. So, any questions before we get going?
How do you calculate the moles of copper product based on the copper sulfate?
See, we don't use the moles of copper sulfate because it's in excess. It doesn't matter how much copper sulfate there is. We want to make sure that the aluminum is limiting. So if we have an excess of copper, that means we can have as much copper as we want, and it makes no difference in the amount of product you're going to get. The only thing that will affect the amount of product you're going to get is the amount of aluminum, because that's the limiting reagent. That limits, copper's in excess, aluminum is limiting. That means that when the reaction takes place, you're going to get all of the aluminum will be used up, and all of it will be converted to product. And so we want just the mass of aluminum to be converted to moles, use that to figure out how many moles of copper you would get from the balanced equation, and then back to grams. So it's just the aluminum is involved.
So in that part of the data table, we would just put basically like that's a trick question, and
no, I mean, you want to make sure. Well, in the table, let's have a quick look at the table. So in the table, does it ask you for moles of copper?
Yeah, based on the copper sulfate.
Right. Yeah. So based on the amount of copper sulfate, and again, that's going to be around 0.1 moles because we have around 100 mils. You'll be measuring out exactly how much there is, just to make sure you have enough. If it's more, if you have 100, just use 100. If you have like 95, then you're going to have slightly less. So you want to look at calculate so what it's asking you, if all of the copper in the copper sulfate was converted to copper solid, how much would that be? So in other words, if you had 0.11 moles of copper sulfate and all of the copper became copper metal, how many moles of copper metal would you get?
0.11.
Exactly. It's a pretty straightforward calculation to do, right? Because there's 1 mole of copper ions for every 1 mole of copper sulfate. So if it all turns into metal, you get 0.11 moles of copper solid. So what you're going to do is basically calculate the amount of copper you would get if all the copper was converted, And then you're going to calculate how much copper you would get if just the aluminum was taken into consideration. And whichever number is less, that is your limiting reactant. And so what we're basically counting on here is that you're going to have less aluminum than copper. And so the amount of copper solid you're going to get at the end will be limited by the amount of aluminum. And that's what a limiting reactant is. It's the one that when you figure out how much product you would get, whichever one is less, that's your limiting reactant. Okay?
Okay. Thank
All
you.
right. All right, so I'm just going to pause for a second. Yeah, everyone get their stuff together and cameras on so we can, make sure you're not catching on fire, and we'll do this together, okay? Just let me pause this for a sec. Okay. So I would like to see, here we go. Hi, Arissa. How are you?
I'm good.
All right, so I'm going to move this down here. All right, so first thing, you're going to want a 4 by 12 inch piece of aluminum foil. Although when I did this last night, I noticed that was slightly too much. You're going to want somewhere between 1.4 and 1.6 grams of aluminum. So, Raj, here's the check and make sure that that's between. So I measured that last night. So make sure it's between 1.4 and 1.6. Oh, wait for it to come on. Oh, there we go. All right, now throw it on there. So what's the mass of the aluminum?
Well, currently it's 1.57.
All right, perfect. So it's just a little bit less than the maximum. So measure 50 mils of the copper sulfate. Be careful, you don't want to splash it on anybody. So far, Arissa's the only one I see doing the experiment. So we need some other folks doing the experiment as well. There you go. So when you measure, you want to get down, there you go. You want to get down to the level of the, perfect. All right, so pour that in the beaker.
So when you weigh the aluminum, are you like cutting it up into pieces or like balling it out?
Before you cut it into pieces, get the mass, and then you can tear it into pieces after. So other people, I'm only seeing Arissa. I want to have some cameras on, please. Go ahead, dump that in.
It has to be between 1.5 and, what'd you say?
I think it's 1.4 and 1.6.
Okay.
Thank you, Nicole. All right, now see if we can get 100. So yeah, just see if we can get another 50 in there. Because every bottle is going to be filled not exactly the same.
So then after you measure it out, then you cut it into smaller pieces?
Yeah. So do we get 50?
Almost exactly.
Oh, perfect. All right, so we have 100 mils of our copper sulfate solution. There you go. And you just put the top back on that. So now we want about 1 gram of table salt. So just plain, any kind of salt. If it's kosher salt, that works too. Doesn't really matter. Can anyone tell me what the salt is for? the sodium chloride? Why are we using sodium chloride in this reaction?
As a catalyst.
What does that mean, a catalyst?
Oh, that means it doesn't change in the chemical. It doesn't chemically change.
Oh man, Arissa, you should be teaching this class, man. That's exactly right. Yeah, a catalyst doesn't change from the beginning of the reaction to the end. It might change during the reaction. There's a lot of catalysts that chemically change during the reaction, but by the end of the reaction, they're turned back into whatever they were at the beginning. So our sodium chloride is there at the beginning, and it's there at the end. So what else does a catalyst do? Why do we need it? If it doesn't change in any way, why do we need it? What does a catalyst do for us? So just wait for it to, and then hit T for tare. You know what tare means? It means basically it's going to calculate the mass of this and subtract it. There you
Do
go.
smaller pieces of aluminum have to be exact?
No. Nope. About 1 gram.
Okay.
So what does a catalyst do? Around 1, doesn't have to be exact.
Yeah, no, just don't
Yeah.
want to get too much because salt is hard to.
There you go. That's fine. So just dump it in there and stir it up with the spoon till it dissolves. What does a catalyst do other than not change? There must be some reason we need it. If it doesn't do anything, we wouldn't need it.
Does it help it react more?
Right, it increases the speed of the reaction. That's what a catalyst does. That's basically the definition, that's one of the 2 definitions of a catalyst. One, it doesn't change from the beginning to the end, and the other, it speeds up the reaction. And in this instance, hopefully someone's read the procedure. What is the salt doing in this reaction? Other than speeding, how is it speeding up the reaction? Yeah, just stir it till. Do you see any more salt? Is it all gone?
No, I don't think I see any.
Okay, then it's ready to go. So then you can just start tearing this up into little pieces. Tossing it in here. What does the catalyst do in this particular reaction? Yes, John. Wish you weren't so shy of using the microphone. Yeah, it removes a layer from the aluminum. A layer of what?
Is it oxygen?
It's an oxide. Yeah, it's an oxide. So aluminum, like most metals, react with oxygen in the air and makes an oxide, where the aluminum is positively charged, the oxygen is negatively charged. Gold doesn't do that. So gold isn't reactive. That's why it's such a valuable. One of the reasons it's such a valuable metal. It stays shiny basically forever because it doesn't react with oxygen. But most metals do. And so if there's a thin layer of aluminum oxide in the aluminum, it basically keeps the copper from getting access to the aluminum inside of it. So you need to remove that layer for the reaction to really start going. Lance, check the procedure, dude. Then just push it down. It should start reacting. Oh, see it going?
Yep.
So what are you seeing, Roger, that tells you that there's a reaction happening?
Well, 1, it's fizzing,
There you go.
and 2, the aluminum is now covered in copper-ish stuff.
Right. So there's 2 things telling you there's a reaction occurring. 1, it's bubbling. So that tells you that there's something happening.
Yep.
And the other is that there's a color change, right? The aluminum's going from this shiny silver color to the sort of dark brown color. What do you think the dark brown is?
Copper.
Yep, it sure is. So I see 4 people. Then everybody else is just what, too shy? Or you having trouble? Do your cameras don't work, or what's going on?
When you add the aluminum, do you like ball it up or leave it like this?
Oh, what do you think? That's a good question. What do you think? If you were to take the aluminum and put it into a big, scrunch it into a tiny ball and throw it in, do you think the reaction would go faster or slower?
Slower.
Yeah, that's right. Why? Why do you think that?
Because it would be denser.
Not so much denser. What do you think it would do to the surface area of the aluminum if you took this like really big, thin piece of aluminum and balled it into like a really small, like we said, dense piece of metal? What happens to the surface area of the aluminum?
Increases.
It decreases when you scrunch it up. And so you want the, oh, feel the sides of it, Raj. What's happening?
It's warming up quite a lot.
Yep, that's another thing that's telling you the reaction is taking place. Temperature, the change in temperature. And so when it gets hot like that, that's telling you that's an exothermic reaction. It's releasing heat. So it's three things that we know. Yeah, it's going pretty good now.
That's bubbling quite a lot.
Yeah, you can see the bubbles sort of. Yeah, so you want to tear it into small pieces. You don't want to ball them all up. You want to get as much surface area as possible, because you want to get maximum contact between the copper in the solution and the aluminum on the foil. And you maximize that by increasing the surface area. In fact, that's how most catalysts work, or a lot of catalysts work, is they, especially ones that involve gases, they increase the surface area on which the reaction takes place. That's how your catalytic converter in your car works. It provides surface area for the gases to react. Yeah, has anyone heard about the gang in Los Angeles who stole like $1 million worth of catalytic converters, and they got caught?
Sounds like they're doing a really bad job.
And that's about a really bad joke. But why are catalytic converters so valuable? What's in them that's so expensive?
It's the type of metal, but I don't know what type of metal.
Yeah, there's rare earth metals in there that are called rare earth metals for a reason. They're pretty rare. And so like there's palladium in there, there's platinum in there. Just the platinum alone is worth a lot of money, but the two of them together, platinum and palladium, are both like really expensive metals. So I think they're both going for like more than $2,000 an ounce. So you don't need a lot of catalytic converters for them to be pretty expensive.
This is supposed to be steaming.
Oh yeah, it's going to get hot. Yep, they're going to get hot.
And murky.
It's really hot.
Uh-huh. Yeah, luckily it doesn't get so hot that the plastic melts. So that would be very bad. Then we'd have to do it in a glass container. Or some reactions are so exothermic you actually do them with the reaction vessel in ice. Sometimes in dry ice, because there's so much heat released that it would break whatever you were doing it in. So, but in this instance, doesn't release quite that much heat, but it's pretty energetic, as you can see.
I think it's almost done steaming.
Yep. So you stir it around, and we'll know how will we know it's done?
When we don't see any more aluminum or just general
Bingo. Yeah.
sparkling.
Yeah. When there's no more shiny bits in there, then we pretty much know our reaction's done.
I can't really tell.
Oh, I'm a bad scientist. So I didn't write down our mass of the aluminum. was 1.56 grams, right?
Yeah.
I'm gonna write that.
Wait, no, it was 1.57.
Oh, excuse me. Okay.
What? They're different.
They are different. Man, you're going to be an analytical chemist. I can tell. Where did I put my pen? Oh, here it is.
Oh, yeah.
So 1.57 grams aluminum.
Yep.
All right, so now we should measure the mass of our filter paper. So here's,
Filter paper.
It's 2 sheets of filter paper. We're just using one, right?
yeah, just using one of them. So yeah, we want to make sure that it's all on. So
Okay.
the 127.
Yeah.
Okay. Okay.
Okay.
Yeah, so we're basically, has everyone got their reaction going at this point? Yes, no?
Yeah.
Pretty hot.
Yeah, so once all the aluminum's gone, give it about, I think it said at least like 5 or 10 minutes for everything, for the copper to settle. Because some of the copper is going to be fairly fine pieces, like, you know, basically you'll see like a suspension of small particles. So you want to give that some time to sink to the bottom.
I can see some.
Yeah, some big chunks at the bottom and some floating on the top. Actually, ew, it's kind of nasty, isn't it?
Yeah. It looks. Ugh.
Yeah, so basically our aluminum and our copper have switched places.
Yeah.
The aluminum was a solid metal, and now the copper is a solid metal. We're sort of let it cool down. And then we're going to decant this solution. What does that mean, to decant something? What do you think? What does decant mean?
You take away its cantiness.
That's right. We take all of its cant away. So it doesn't have any cant left. So when we decant a solution, what are we doing?
Like straining it?
Yeah, basically. Yeah, I mean, we're not,
Oh, shit.
basically it means we're just pouring off the liquid
No, this is not it.
and trying not to pour off the solid. So like when you decant a wine, for instance, if there's like, you know, schmutz at the bottom, you're trying to get the liquid out and leave the solid behind. In this instance, we're doing the same thing, but we're throwing the liquid away and we're holding on to the solid, because the solid is the product we want. So we just slowly pour it, and you can pour it in whatever container you want. Slowly pour it so that the liquid is gone, the blue liquid's gone, but the brown solid remains. And then we're going to rinse it with water a couple times. So why are we bothering to rinse the solid with water? Why don't we just go ahead and filter it and be done? What's the point of rinsing it with water?
There will still be aluminum sulfate in there.
That's right, man. You're all over it today, Marissa. Yeah, you want, when you dry out the copper, that's the only reactant, the product you want left. Remember, there's two products to this reaction. There's solid copper and there's aqueous aluminum sulfate. And if you don't rinse all the aluminum and sulfate ions away, they're going to dry out and turn back into an ionic solid and add to the mass of your product. And you don't want that. The only product you want is copper.
It's turning kind of pink.
Oh, the copper's turning a little pink color?
Yeah.
Oh, yeah. Hi, Jerome. So,
If it's
Oh, go
done,
ahead.
steaming?
Go ahead. I couldn't hear you.
If it's done, will it still be steaming?
It'll eventually cool down because what's happened is all the aluminum's gone. So now the reaction is done, right? Notice you still have the blue color, meaning there's still some copper sulfate in the solution. So basically you want to rinse the copper sulfate away. You want to rinse the aluminum sulfate away. You want to get rid of everything except the copper itself. So yeah, that's why we just sort of give it like a few minutes for it to cool down and let the copper precipitate, and then we can start decanting it, rinsing it with water and filtering it.
And when you prep this, you're supposed to cut this part off?
Oh, we don't cut. No, I'll show you how to do that. We'll do that now, actually, because people are probably getting ready to start decanting and washing. So for the filter paper, you just first fold it in half, then fold it in half again so that you've got
A fourth.
a quarter. Yep. Now there should be 4 layers in there, right? We've got 4 layers since we've folded it twice. Just get that first layer and pull it out so that you get a cone.
Like a cup, like that.
Yep. And then just drop that. So take the mass of that. Remember to record the mass of that, so that when you put it in the funnel, it will fit perfectly. And then you can go ahead and just wet this with a little bit of filtered water. When you wet it with a little bit of filtered water, it'll stick better. Excuse me, it'll stick a little bit better to the filter.
Professor, could you repeat again?
All right.
Okay.
So fold it once,
Uh-huh.
half, and then twice in quarters, and then hold it by the pointy end here. So we got the pointy end. Hold it by the pointy end, turn it upside down,
Okay.
and you should have 4 layers, right?
Yeah.
So just put your finger in like the first one. So here I got the first layer, and just pull it out and do a cone.
Oh, okay.
So now I've got a cone.
Yeah.
Okay, got it.
Excellent, Raj.
Okay, thank you.
No worries.
Done.
Yeah, and then it should fit perfectly in the filter. So I'm going to get a big container for us to like dump all this stuff into, and get us some filtered water.
Mhm.
No, this will work.
Okay. So
All right. So I've got some filtered water to do our rinsing with. And yeah, so what you want to do now is to slowly pour the liquid from this into here. Try not to get any of the solid out, just really slowly. There you go. If you lose a little bit, that's fine. There you go. Perfect. No rush to this part.
And the blue liquid, like we don't have to save. It can just go anywhere.
Nope. And that can go down the sink too, because there's nothing, we don't have anything toxic in these kits. So it's just copper, it's just sulfate ion. It's perfectly fine. Dolphins aren't going to get angry. Is that most of it?
mostly. Yeah.
Oh man, that's quite a lot of product, isn't there?
That is quite a lot of product. That's almost all of it.
Okay.
Yeah, that's probably.
Yeah, so get like 25 mils of water. And we'll rinse this a couple times. Oh, actually, why don't you just fill that up and I'll dump it up because there's still some copper in there. So I'll rinse that out for you.
I'll be right back.
All right, there you go.
So then, is this what it should look like? Oh wait, my camera's not on. Is this what it should look like after you pour the blue stuff out?
Yep, exactly.
Yeah.
Mm-hmm. Yeah, so we're just going to rinse it a couple times, and then we're going to start filtering.
Does the amount of water have to be exact?
No, not at all.
That's pretty good. I need a towel.
Oh, yeah.
You're rinsing it without the filter first, right?
Yes, we're just rinsing it in the beaker, and then once we've got all the stuff in the filter, we'll rinse it a couple more times. All right, so just pour it on top of the copper and just swirl it around. Because we're just basically washing all of the salt off of the copper now. And just give it a good swirl. There you go.
Okay, that looks pretty good.
All right. So let's decant it again. Okay, we'll filter it in a second. We want to do 2 washes.
This one's a bit hard.
Is the copper moving around a little bit now?
Yeah, there's just a lot more.
Yeah, if you lose some of those like tiny little particles, it's not a big deal. It's basically part of the exercise is to figure out. I mean, we're going to lose some. That's just any chemist. You're never going to get 100%.
That's pretty good.
All right, one more time. So here's a question for everybody. If you do your calculation, let's say you calculate, you should get 3 grams of product. You should get like 3 grams of copper. If you get more than that, if your yield is more than 100%, what happened? Is that a problem? We can have a little bit more, it's fine.
That means you didn't let it dry all the way, right?
Yeah,
So
there's a couple of things that could have, yeah, just dump that and rinse it again. Yeah, so there's a couple of things that could have happened. One, you didn't let it dry out enough. And so the additional mass is from water. What's the other thing that could have happened? Did you swirl it around?
yeah.
Okay.
How many times do we rinse it without the filter?
I don't know, it's in the procedure. Is everybody else doing it with us, or are you just watching? Francesca, are you helping? Are you doing it?
I usually do my experiments on Thursdays because those are my days off.
Oh, okay.
Yeah.
What about you, Gordon? Are you working on it? I know Xiaoyi's working on it.
Yes, I do now. I'm doing now, but I
Okay.
just waiting the copper is thick.
All right. Oh man, this looks really good, Raj. All right. So now we can start our filtering. So, so the tricky part is trying to get this into there. So what we're going to do is
So where are we filtering it? Okay.
right there. So just wet this with a little bit of water so that it doesn't move around on us. We want it to sort of stay put. So that'll help it stay put. All right. Excuse me. Now you can use the spoon and just sort of scoop it into the funnel. So just put it right over the. There you go.
So before we use the filter, it said to add 20 milliliters of water.
Yeah, just you want to wet it just to make sure. You're adding
I like
the
that.
20 mils of water. You're adding to the copper to rinse it. Yeah, it's a terrible sound, right?
And then with the water in it, you're pouring it into the funnel, right?
After you've decanted it, so you rinse it a couple times, swirl it around. There you go. Now to get the rest, you can just dump some water in there, swirl it around real quick, and then into the filter. There you go. Perfect. Oh, don't let it go up too much. There you go. Excellent. Good job, Raj. You still have some in there. There you go. Still a little bit in there, so you can just keep doing that. Just keep adding a little bit of water in there. Give it a quick swirl. You can even mix it up with the spoon. Try and get it off the sides. And when you're trying to get all the copper out, the other thing you can do is just you take one of these transfer pipettes, fill it with water, and basically squirt it out around the sides of the container to make sure you get all the copper off the sides. There you go. Great job. So if there's any left, basically squirt the side of it. We can also squirt the spoon because there's also some on the spoon. And swirl, 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 swirl. Dump. Dump kind of quickly so that the, there we go.
Okay.
Yeah, I think, you want to get that? Do you think we should bother with that?
I think we can just get some off the top.
Oh, there you go. That was a good amount.
I think.
Excellent.
And then there's quite a lot on this thing.
Okay, so to get that off the spoon, we can just hold the spoon right over and just spray it right into the. Some of the, I mean, I don't think some of this just isn't coming off. So
Yeah.
you're just going to have to. So this is one of the things, whenever you do an experiment, you put down sources, potential sources of error, because there's always going to be error. So this would be a potential source of error. The fact that we've got copper stuck to the spoon and we can't get it off.
Yeah. But I think we did pretty good.
Yep. So now dump this out. Notice it's a little blue.
Yeah.
Yeah. It means there was some copper left over. Some copper ions, which are blue. to make them easier to spot. So now we can just rinse this with water like 2 or 3 times.
So just pour some.
Yeah, be careful pouring it
Yeah.
in. You don't want it to overflow. Yeah, that's the thing when you're pouring, you got to commit.
Yeah.
If you don't, it'll just run down the side. So if you're going to pour, you got to pour. There you go. Luckily, it's filtering pretty quickly. So
Yeah.
once you've washed the filter like 2, 3, 4 times, then basically you're done. What you want to do is take the just leave it in there for as long as you can, so that all the water drains out. Then take the filter paper out, sort of spread it out, put it on a plate or something like that, and just leave it someplace warm and dry overnight. If you're in a hurry, you can put it in your oven at very low temperature. Like I think 225 is as high as you want to go. Any higher than that, you run the risk of the paper starting to burn or brown, and we don't want that.
Will leaving it in the sun make it like mess it up?
No, it shouldn't, because theoretically the only thing in there is copper. I mean, I guess it could oxidize. The sunlight could help it oxidize a little bit. So that might be another thing. It would add, if it does oxidize, and because it's moist, there's oxygen dissolved in the water, which will then become in close contact with the copper. So that's actually another way that it could increase in mass. It could oxidize. So then you get the mass of oxygen along with the copper. But yeah, so I'd probably, I mean, it shouldn't make that big of a difference. I was thinking of putting it in this, like in a dry, dark place overnight. Someplace where dogs won't eat it.
Yeah.
Man, it still looks a little blue. Or maybe could be just, I think all the liquid looks a little blue with this particular shade of plastic.
Yeah, from here, pretty much everything, it looks uniformly blue, so I think it's just the
I think it's just the
plastic's a bit
plastic.
blue.
Mm-hmm.
Your son talks like he has a PhD. It's the funniest thing ever.
Well, I mean, he is 11, so you know. He'll be teaching the course in the summer.
Oh, definitely.
That's what he's doing for his summer vacation. Right, Raj? You're going to be teaching 210. All right,
All right, there's
one more rinse.
Yeah.
And we'll start putting all this stuff away. So next week, we're going to be doing a lot of reactions. So it's really important. And some of them involve fire. So I would like to have more people with their cameras on, because I want to make sure you're not catching on fire. So if you've looked at the procedure, I think we're doing 7 chemical reactions. And I did this with the 410 group last week, and yeah, it's kind of chaotic because there's so much going on.
So this stuff, even though it has copper in it, it can go down the sink.
Yeah. Copper is not. Well, I mean, it's an essential nutrient. Actually, your body needs a certain amount of copper. So
just don't eat that.
Just don't eat that. Yeah, exactly.
And then when the copper is all dry, I can throw it in the trash.
Yep. So can anyone explain why the color changed from blue to brown? What happened to the copper when when it was blue, it was one thing. And then now that it's brown, it's another thing. What was it? What state was it in when it was blue?
AQ.
It was what?
AQ.
It was aqueous. It was an ion when it was blue. And now that it's brown, what is it?
A solid.
Mm-hmm. But what, it's not only is it a solid, is the copper an ion now?
No.
No, what is it?
An element.
It's always been an element.
Maybe it's a copper.
It's what?
It's a copper without the electron. I mean,
Well, actually, it has its electrons back. In solution, it's a copper ion. Now that it's a solid, it's a copper what?
Atom.
Atom, exactly. It's neutrally charged. It doesn't have a charge anymore. And so it's the loss of those two electrons that changes the outer shell of the copper. Copper, then remember, everybody wants to get a full outer shell. And so when copper loses those two electrons, it then has a full shell. And it's the movement of those electrons that gives it that blue color. In fact, a lot of transition metals, when they lose their electrons, you get these beautiful color. Like cobalt gets, you probably heard of the color cobalt blue. It's even darker than copper. It's this beautiful blue color. And lead, unfortunately, this is beautiful yellow color when it's charged. And that's why it was used in paint for so long, because it makes this beautiful, beautiful yellow.
It also makes people dead.
And that too. And chromium, which is incredibly toxic, makes a beautiful green color. So that's why a lot of painters in sort of, died at early ages back in the Middle Ages and later, because they were using these colors made out of like extremely toxic transition metals, but they were really pretty. So, at least they died for something, right? So if you're done, you can click off. Are there any other questions before we call it an afternoon? I would like to thank my assistant who did a fantastic job. Great job, Roger.
Yeah.
Anybody else have a question before we go?
Do I throw this away or put it in the lab kit?
Oh, that you can just recycle that.
Okay.
Yep. Yeah, they're not going to want that back.
Okay.
I don't think they refill them because they can't really guarantee that it's completely clean. So it's just easier making a new bottle, I think.
Yeah.
Okay.
Yeah, I'm pretty sure. I'll double check, but I'm pretty sure. Yeah, we don't need to keep that.
Thank you.
Thank you, Arissa. Thanks so much. You get a participation ribbon today, for no doubt. All right, I'll see you later.
All right. Bye.
Anybody else have any questions before we go? Nope. All righty. I remember if you want to come by office hours, they're on Wednesday, which is tomorrow.
Yep.
And then we'll be doing our next recitation on Thursday. So I will see you then.